In this video, we'll discuss Euler's method, a numerical technique for solving differential equations. Although it's showing its age a bit, it was published in 1768, it is relatively easy to understand, and many of the more modern methods are directly based on it. Euler's method is itself based on the linearization, which we might remember from calculus. The linearization of a function near a point is simply the tangent line through the point. Y equals y0 plus f prime of x0 times x minus x0. Tangent lines can be used to approximate functions. You see that near this point, we cannot visually distinguish the line from the curve. Suppose we have an initial value problem. dy dx equals f of x comma y. And an initial condition. This curve goes through the point x0 comma y0. We want to find an unknown curve y. So maybe y looks like that, but the only point we actually know is the initial condition. x0, y0. We can plug this point into f to get the derivative, and that's enough to linearize around the initial condition. And on a small interval near the initial condition, this linearization is a pretty good approximation of the curve. It is starting to break down a little towards the end of this interval. So, what's the equation of this line? Y equals, give myself a little more space, y equals y sub 0 plus f of x sub 0 y sub 0 times x minus x sub 0. Now, it's easy to get confused here because you're used to taking a derivative when you do linearization, but this f is already the derivative, so we don't need an f prime here. But that's only on a small interval. What if we need to approximate y on a larger interval? Clearly, this approximation stops being a good approximation of the curve pretty quickly. Let's build up our approximation. In particular, let's approximate y on x sub 0 plus h to x sub 0 plus 2h. We'll use the same linearization method we just used, but some difficulties now arise. We don't have an initial condition. In particular, we'd like to linearize around the first point in the interval, just like we did over here, but we don't know what this point is. However, we've approximated this entire curve on this interval with this tangent line. We can certainly approximate to this point like so. So let's let x sub 1 be x sub 0 plus h. We'd like for y sub 1 to be this y coordinate. Y sub 1 equals y of x sub 0 plus h. But we don't know what this is. Instead, we'll approximate. Y sub 0 plus f of x sub 0 y sub 0 times x sub 0 plus h minus x sub 0 equals y sub 0 plus h times f of x sub 0 comma y sub 0. So we took this value and plugged it in to our approximation. We can now approximate the derivative here. F of x sub 1 y sub 1. And now we have an approximate point and an approximate derivative, and we can linearize on this interval x sub 0 plus h, x sub 0 plus 2h, y is approximately y sub 1 plus f of x sub 1 comma y sub 1 times x minus x sub 1. And we can repeat that process. So if we wanted to approximate on a third interval, we could do so. That then is the idea behind Euler's method. On each interval, we linearize around a point and use that linearization as our approximation. Be aware that the further away from the initial condition you get, the worse the approximation becomes. We'll discuss error in the next video.